So here's an old exam question on second order differential equations. It looks much harder than it is, and it's certainly suitable for Edexcel FP2 of modern times, even though the question probably dates back to the 80s. So if we first of all, we're given a substitution y equals z cos x. So if we differentiate that, now I should say at this stage that we really do not want to be making hard work of differentiating. So if I differentiate the z first, then I get dz by dx times by the cos x. Then if I differentiate the cos x, I get minus sin x times by z. Okay. Now I'm going to use the that's dy by dx, of course. Now I'm going to use the chain rule again to differentiate a second time. d2y by dx squared is equal to, now I'm going to differentiate the dz by dx to get d2z by dx squared, times that by the cos x. Then differentiate the cos x, which is the minus sin x, times that by dz by dx. I have only done the first part of this expression there. Now I'm going to do this part of the expression, differentiate the z, I get dz by dx, but that's times by sin x. And differentiate sin x, I get cos x. But that's just times by z, and it's take away because I'm taking away the whole thing. I may as well combine the whole thing here because I've got some like terms going on here. So let's just bring those two together. Cos x, it is a good idea to, because this is the next stage is going to be at one long line. So if we can reduce it a little bit by in any way, then we really do want to be tidying up our algebra as much as we can before we go. One of the worst mistakes people who are less experienced with algebra is not to simplify as we go along. Okay, so now I'm asked to go from here to here somehow. So I really need to write this line out to show that I'm going to get from there to there for using the expressions that I've just got. Okay, so I'm just going to do that now. So what I want to be doing is substituting in my expressions into this equation here. It's going to be quite a long line this, but hopefully it will break down and we will get to this. So that's quite a long line of algebra. If we, before multiplying out, can break it down a little bit, so to avoid having to write so many terms out, that might not be a bad thing. I'm aware that there's no term in dz by dx here, so it would be quite nice to look to see if that term at least cancels. I can see it does, because I have cos squared x times by 2 sin x dz by dx there cancelling, with the same term, the equivalent term there, which is 2 cos squared sin x dz by dx. They cancel. It's still going to be reasonably a reasonable way to go, but I'm now going to multiply out and hope it breaks down a little bit further. So I've got cos cubed x d2z by dx squared minus cos cubed xz minus 2 cos x sine squared xz plus 2 z cos x equals cos cubed x. Okay. Now at this stage it's looking quite promising because I have got rid of dz by dx and I can see a sine squared here, which can replace with 1 minus cos squared, and hopefully it will break down. I can also see a common factor of cos x. I'm going to take that cos x out. It's not a big thing, but I'm going to do that. And I think when we're so close to the final outcome, we would probably be wise to take a deep breath and make sure we're not going to write anything silly, because of course we have been asked to show that this result is true, so we really do need to cos squared x. There is an x in this term as well. There was an x there and there's an x there. It's a bit messy, so okay. Now, so it's not done a lot really. I can replace my sine squared with 1 minus cos squared. So I've got cos squared x d2z by dx squared minus cos squared x z minus 2 1 minus cos squared x z plus 2z is equal to x cos cubed x. And much like I said before, it's as well to look for cancelling things here, and that 2z cancels with this, well, that z here should be outside the bracket, of course, this 2z here. Okay, let's rewrite that actually carefully. So basically, what I'm saying is, now that I've got the z outside as it should be, this 2z here cancels with that 2z there. Okay, so if I now multiply out again, it's getting close now, cos squared x d2z by dx squared minus cos squared x z plus cos squared x 2 cos squared x z is equal to x cos cubed x. So we can see that that cancels down. I think we can see, we've done so much work, we might as well write the whole line out. So we've got cos squared x d2z by dx squared plus z cos squared x equals to x cos cubed x. Now I can cancel my term in cos squared. So I finally got to the point I wanted to go to, the expression here, d2z by dx squared plus z equals x. There wasn't that much in that, just a little bit of persistence and a little bit of confidence and accuracy. Okay, so let's go to the second part, just do a little bit of rearranging of the screen here. Right, so for the second part we're more into the routine of just solving second order differential equations. We can see the auxiliary equation for the equation we've just found is m squared plus 1 equals 0, which gives us m is plus or minus I. That gives us a complementary function of z, because it's the variable we're dealing with, a cos x plus b sin x. Okay, now we need to find a particular integral. We've got a term in x here which is linear, so we try y equals to ax plus b because it's linear. It should work, because there's no reason why it would coincide in any way with our complementary function, so it should be fine. Now if we differentiate y, we just get a, and if we differentiate again we get y double dot is equal to 0. So when we shove it back into this d2z by dx squared plus z, I said y, but of course I mean z there. When we put it back into there, we've got, so we've got z is equal to ax plus b, and this d2z by dx squared is 0. So we just have ax plus b equals to x, so that gives us a equals 1 and b equals 0. Okay, so that gives us our general solution for y, for z, is z equals to a cos x plus b sin x plus this complementary function we've just found, which is just x. Okay, because a is 1 and b is 0. Right, so now we can use some of the information. We're told that when x is equal to 0, y equals to 0. Oh, let's write it in terms of y now, actually. So we've got y, if we sub for z, we've got z is equal to y sec x. So we're back with the variable we started with now. So y sec x is equal to a cos x, b sin x plus x. Let's multiply that out. Y equals a cos squared x plus b sin x cos x plus x cos x. Okay, so now that so that's that. So now we can use it when x equals to 0, y equals to 0. That gives us 0 is equal to, well, this is going to be a times 1 plus b times, that's going to be 0, isn't it? Because sine 0 is 0 plus 0. So that gives us a is equal to 0. Right, so we've got a is equal to 0, but what about b? Well, we're going to have to differentiate because we're told the value dy by dx when y equals to 0. So let's differentiate our term. But let's write it out now with our slightly, because we've taken the cos squared bit out now. So let's write that out now and differentiate that, because it's going to break it. It's going to make it easier. So now let's differentiate again. Differentiate this. We get dy by dx is equal to, right, that comes to be cos squared x minus sine squared x. That's basically that's sine 2x differentiated to cos 2x, which is what I've just written, cos squared minus sine squared. Then product rule on this, that's plus cos x, because that's x differentiated is 1, minus x sine x. So now I can just say when y equals to, when x equals to 0, dy by dx equals to 1, because that was what's given in the question, when x equals 0. So we can put that in, so we get 1 is equal to b times, now that's going to be 1, the first term, take away 0, because sine of 0 is 0, plus 1 minus x sine x, or not x sine x, well obviously we're subbing in, so that's minus 0. Okay, right, so that actually, when we work that out, gives us b equals 0, which is, after all that, we've got a is 0, b is 0, so all of this is gone. So we finally left out with what we worked out as our particular integral in the first place. We've done all that work to find our particular solution given the conditions is y equals x cos x. And that's it. Long, and you just need to be accurate. Okay, bye.